all that good stuff. And we end it here. All right. So I think we ended here. Well, we didn't end here, but we were walking through this and we were talking about electron configuration and the principal quantum number and so on and so forth. So we left off talking about the different types of orbitals and how many electrons each orbital can hold. And that's two, how they have to be paired up, one with the spins, opposite spins, how the p orbitals are organized, how orbitals are not real, right? They are equations of, they are the graph of an equation of the path of an electron around the nucleus. And we talked about the s, p, d, and f orbitals and how many electrons total are possible for those orbitals and how many electrons each orbital can hold, all that good stuff. All right, so what does that mean? Well, when we think about this in terms of, because there's some nuance to this. And when we think about the electrons, let me say this, right? Remember, we're talking about shells, right? So this would be considered like the first energy level. You can see that here, first energy level. And then in the second energy level, we change colors. That will be here, right? And you can see that here. Uh-oh, didn't try to do that. Right? And that has a 2s and 2p. So you can have a total of 8 electrons there. And in the third energy level, oh, let me pick a different color. In that third energy level, which is right here, right? That's my third, so that's 3s, 3p, and 3d, right? So D can hold 10, P can hold 6, and S can hold 2. So you got a total of 18 electrons that can be there. 8 electrons in the second, and in the first, 2 electrons in the first. So this is the way to think about this is to think about in terms of where those electrons are, right? And if this was an atom with a full complement of electrons, the only electrons that would be reactive or that would get touched will be the ones here. So this, the very last shell, in this case, it's the third energy. It could be any energy level, depending on the atom. But that very last shell is what we call the valence shell. We'll say it's the outer electron shell. Right. So that last shell is what, those are the electrons that are responsible for reactivity for any atom. Any atom, it doesn't matter what it is, how many electrons it has, the valence electrons are the electrons that control its reactivity, how it interacts with other atoms and so on and so forth, right? So every orbital can hold 2 electrons. So if we were to fill this up based on the model that's over here, we say that this is 1s, right? We'll fill that up, and then 2s, we'll fill that. If you notice, the 2s is a little bit lower in energy than the 2p. And so we'll put 2 electrons in that before we touch the p, right? And then we'll do this, right? Fill up that before we touch 3, right? And then in 3, you see 3s and 3p are lower. 3s and 3p a little bit lower in energy, so we're going to go here, right? And then 3p, we'll fill that up. And then it said 18 in the third energy level. So that's 6 in 3s and 3p. And then we could also put in here 10 in 3d. Right, so that's what the configuration would look like if this was an atom, whatever atom it may be, and it had a full complement of electrons in every orbit. Right, notice again, the spins are opposite, and every degenerate orbital, I put in 1 electron before I put 2 in any. Right, so when I'm filling up P, if I have 5 electrons, I'm putting in 3, 1 in each orbital, and then I'm coming back with the other 2 and distributing those between the P1 and P2. Right, there's a concept with especially when you're talking about carbon and valence bond theory. There's a concept what we call hybridization, where you can actually take the orbitals and add them together. The 2s and 2p, you add them together and you get what's called hybrids, and you redistribute all the electrons. But we're not going to talk about that. We'll talk about that in organic. So right here, again, the principal quantum number n, if it's 1, there's only 1 sublevel. So you can see that that's 1s. If n is 2, then you got 2 sublevels, s and p. N is 3, you got 3 sublevels, 3s, 3p, 3d. If n is 4, you have 4 sublevels, 4s, 4p, 4d, and 4f, like that. And remember how we thought about this the other day, right? We said that you have in the first energy level 1s, and then the second and the 7th are identical, 2s, 2p, 7s, 7p. And the third and 6th are identical, right? 3s, 3p, 3d, 6s, 6p, 6d. And then 4 and 5 are identical. So when we're filling this up, we're going in this direction. Let me show you over here, because this is a better diagram for showing that. So we're filling up like in this direction here. So we're going from here to here, and then here to here, and then we're going from here to here. And then notice the 4s is in the 4th energy level, but the 3d is here. So when you're actually filling these, the 4s actually comes before 3d, even though 3d is in the 3rd energy level. There's a really, really specific phenomenon called orbital penetration, where 3d is filled before, I'm sorry, where 4s is filled before 3d, but we'll worry about that when we get to it. All right, so we're going here and then here, and then we just follow that all the way down, right? That's why I like this diagram, because it shows you how to fill the orbitals. All right, so if we go back to here, let's talk about the quantum numbers, because we need to know that. All right, so we already talked about n, because this is going to help us as far as knowing where electrons are in any given atom at any given moment, right? Well, we can't know everything about it, right? That's the Heisenberg uncertainty principle. You can't know everything about every electron in a given atom, right? But you can know some things about the electrons, all right? So n is the principal quantum number. That can be 1 through 7. L is the angular quantum number. So that describes the orbital shape. And depending on what type of orbital you're dealing with, S, P, D, or F, L is going to be either 1, 2, or 3. All right, that's the angular quantum number. So for a P orbital, L is 2. I'm sorry, it's 1. For a D orbital is 2. For F orbital is 3. For S orbital is 0. And then there's the magnetic quantum number, M sub L. That describes the orientation of the orbital. And that is plus L to minus L. I'm gonna show you what that means in a minute. So let's say L is 3. So that means that the magnetic quantum number is going to go from -3 to -2 to -1 to 0 to +1 to +2 to +3, like that, right? So it's -L to +L. And when we look at these examples, you'll see exactly what I'm talking about. And then there's the fourth quantum number, which is the spin quantum number. So it's +1/2 was -1/2, right? So +1/2 is a upward spin. -1/2 is a downward spin, right? So we have to know these attributes of electrons, and we have to follow rules, right? So there's the Pauli exclusion principle that says no two electrons in a given orbital. So that's paired up together, will have the same four quantum numbers, right? So knowing that, just having a different spin number allows us to stay within the bounds of that principle, right? As long as the electrons are paired up and have opposite spins, then they're going to have four different quantum numbers. The N, L, M sub L, M sub S, all are going to be, even if N and L and M sub L are the same, as long as M sub S is different, then that follows the Pauli exclusion principle. And then for Hund's rule, that we talked about that already, one in each before two in any, if you're dealing with what we call degenerate orbitals, or orbitals that have the same energy. If all the orbitals have the same energy, you got to put one electron in each one before you put two electrons in any one. All right. So let's do an example real quick. So it says in this example, identify the four quantum numbers for a 3p5 electron. Right. So 3, we know right from the break that 3, that's N. So N is 3. Right. And then it says a 3p. So L is going to be 1, right? Because for L is 0 for S, 1 for P, 2 for D, and 3 for F. And then once we know L, we can determine M sub L, which is again that angular quantum number. And that's -L to +L. So if L is 1, then M sub L is -1, 0, and +1. Right? Now the M sub S, and let me do this. So again, we got 3p5. So we have, this is the completed one, but I want to show you how we would do this. So this is 1, 2, 3, 4, 5. So all the quantum numbers will be the same. So this is -1, that's 0, that's +1. Right? So the quantum number for 3p5, which is this last electron that I put in, the four quantum numbers are going to be N is 3, L is 0, M sub L, I'm sorry, L is 1, M sub L, hold up, M sub L is 0, and then M sub S is -1/2. So N is 3, that's that means it's in the third energy level. L is 1, that means it's in a p orbital. Right? M sub L is 0, which means it's in the middle orbital in that of those 3p orbitals, whether it's px, py, or pz. Let's go back up to here. I think it's pz. Yeah, it's pz, because you can see that p0 is pz, p-1 is px, and then p1 is py, right? So we'll say that M sub L is 0, means that orbital, that electron is in the pz orbital. And then with the minus 1/2 means it has a downward spin. All right, so any electron, we can figure out the quantum number. If we know the type of orbital it's in and the energy level, everything else stems from that. The M sub L is a consequence of the type of orbital that it's in, and the M sub S is a consequence of whether the electron is facing up or facing down. And then the principal quantum number has to be given. It can't just be a random electron that doesn't have any quantum numbers. As long as we know the principal quantum number and the type of orbital, we can figure out the other two quantum numbers. All right, questions about that? All right, let's do another one. So this says identify the 4 quantum numbers for 4D4. So let's draw this out. And we're gonna do it by hand. I have it on here, but I also want to do it by hand. There are 5D orbitals total. And it says 4D, right? That means the 4th energy level. That means N is 4. The principal quantum number is 4. And then it says D. So S is 0. L is 0 for S. It's 1 for P. It's 2 for D. So L is going to be 2. Once we know that, we're home free, because all your other quantum numbers, the M sub L and the M sub S, we can figure that out. M sub L is going to be a consequence of what L is. So if it's 4D4, so we put those electrons in, and again, these are degenerate, so I'm not going to put 2 electrons in any one of those orbitals. I'm going to put 1 in each before I put 2 in any. So this is -2, -1, 0, +1, and +2, right? So now this is the electron in question. So for that one, M sub L is +1, and then M sub S is +1/2 because it has an upward spin. Has an upward spin. All right. So if we wanted to give the 4 quantum numbers, we would say that N is 4. We would say that L is 2. And then we would say M sub L for that 4D4 electron. Now, it's the last electron in that series. We'll say that M sub L is +1. And we'll say that M sub S is +1/2. Right? So any given electron, we can figure out the 4 quantum numbers for. But what we don't know and we can't know is we can know all 4 quantum numbers, but we might not know where that electron is in space. Or we might know where it is in space, but not necessarily know one of the 4 quantum numbers. So that's the Heisenberg uncertainty principle, is that you can't know every single thing about an electron in a given atom or element, right? There's always some one factor that's going to be unknown about that particular electron. All right, questions? Any questions? Any questions about anything? All right, now we need to apply this. So we're going to take some atoms and we're going to figure out what their electron configurations are. We're going to fill these orbitals up and we're going to figure out what they are. So let's do sodium first. Sodium is Na. What is the atomic number for sodium? Anybody? Just look it up on the periodic table real quick.
$11.
11. All right, good. That means it has what? 11 protons and 11 electrons. This is not an ion, it's just an element. So it has 11 protons, 11 electrons. So we need to put those 11 in over here, right? So we'll put this in here. That's 2. That's 3, 4, right? And now I'm going to do this 1, 2, 3. So that's 2, 4, 5, 6, 7, and then 8, 9, 10. And then I'm going to go up to 3s and put that here, 11. Right? So the electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. That's how you would write that out. Oh, my 6 got deleted. All right. Any questions about that? So that's the electron configuration for sodium. 1s2, 2s2, 2p6, that's 10. And then 3s1 gives 11. What group is sodium in? On the periodic table. What group is it in?
Group 1.
It's group 1. So what this electron configuration tells me is this. All right, now look at the numbers. N is 1, 2, 3. So the highest energy level, N is 3. What that means is that these are my valence electrons. These are the electrons that either get given away, or that's the orbital that can accept electrons. So knowing that, you can see why this is a group 1 element. That 1 means something in group 1. So the 1 in group, the 1 in group 1 means that there is 1 valence electron. All right, everybody following that? That's what that, when we group these up, that's what the group numbers mean. So group 1, group 2, transition metals, and then group 3, group 4, group 5, group 6, group 7, and then the noble gases are in group 8. Every atom, when it's reacting or when it's bonding with other things and making compounds with other atoms or molecules with other atoms, it's trying to emulate the closest group 8 element, so the closest noble gas, because it wants to have 8 valence electrons, just like the closest noble gas to it. We're going to talk about that later when we talk about Lewis structures in the octet rule. But everything wants to have 8 valence electrons. It's not always possible, especially for group 1 elements like sodium. So a lot of times what they do is give away their electron. So they just become a cation, and then they just find something that's negative and hang out with it and make a salt with it. All right. So the valence electrons control the reactivity of any atom. All right, let's do another one. Let's take, let's pick something in group 2, and let's do that. I'm just gonna copy, can I do that? Let me see something. I wanna copy this and just use it again so we can see how to fill it up. Shucks. Hold up, I know what to do. Let's see. next. All right. Somebody give me a group 2 element. Just pick one. I know we're gonna do the other ones down here too, but I wanna just pick one of those.
Calcium.
All right, let's do calcium. What's the atomic number?
20.
20. All right, great. So it's got 20 electrons. It's got 20 protons. So let's start filling it up, right? We're gonna go here. We gotta put in 20 electrons. So we're going here, 2 here, 2 here. That's 10. All right, and then we're gonna go here, put 2 here, and then put, so that's now 12, 13, 14, 15, 16, 17, 18. And then now here's the trick, right? Because the 4s, even though it's in the 4th energy level, notice it's lower in energy than the 3D. So we're going to put those last 2 electrons in 4s, not in 3D. Did y'all catch that? Right? When you look at the actual buildup itself, let me go back to here. And I kind of mentioned that a second ago. You see how the 4s, even though it's in the 4th energy level, you go from 3p to 4s to 3D, because 3D is a little bit higher in energy than the 4s. All right, so let's go back to here, and let's put those last 2 electrons in 4s. All right, so we did that. So that's 20 electrons. So the electron configuration for calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What's the valence shell here? Right? What's the highest quantum principal quantum number? N. It's 1 here, 2 here, 3 here, and then 4 here. So my highest valence, my highest energy orbital out of all of these is this one. So where N equals 4. So these are my valence electrons. Right? So now calcium has 2 valence electrons. And what group is that in again? Was that you, Calvin?
Yeah, that's group 2.
Group 2. You see how that matches up? Group 2 has 2 valence electrons. It means that in the outermost shell of any group 2 element, there are going to be 2 valence electrons. That's why when we were looking at, when we were studying compounds, right? And certain atoms always form the same type of ions, +2, +1, +3. That's because it's the valence electrons that get lost. And so for metals like calcium is only going to give you a +2 ion because it only has 2 electrons that it can lose. The other electrons are low in energy, so you can't really touch them. They're lower in energy. So it's always the highest energy electrons that get touched. All right. So those valence that's why I say valence electrons control reactivity, because always the highest energy electrons that get touched or that get shared or that get given away in oxidation, or it's that shell that you donate electrons into for reduction, and so on and so forth. All right. Any questions? All right, let's do chlorine. Man, that spider is huge. I apologize for that. I'll edit that out. That thing is huge. I had to take care of that. All right, let's do, let me see. The same thing I did. Copy. That's not what I said to do. All right. Let me erase this, and then we're gonna do chlorine. And believe it or not, if you can do the electron configurations, it makes determining reactivity a whole lot easier, especially when you get to classes like organic, where you can figure out like what electrons are going to be shared, where the bonds are going to be formed. Because even with bonding, all of your bonding takes place in the valence shell, right? If you're approaching bonding from a valence electron theory, valence bond theory, it just says that when valence shells overlap, you can make covalent bonds. There's another theory, molecular orbital theory, that kind of approaches the same thing, but a little bit differently. But we're not going to get into that for this class. All right, let's do chlorine. Somebody tell me what the atomic number is for chlorine.
17.
17. All right. All right, so let's do that. So that means it has 17 electrons and 17 protons. Right, so we're gonna start here. 1s2, 2s2, 2p. We're gonna go ahead and fill this up. 2p6, that's 10. And then we have 3s2. How many we got left? That's 12, right? So we have 5 left, is that right? So we're gonna do this, 3, 4, 5. Anybody not following that? So this is gonna be 1s2, 2s2, 2p6, that's 10, 3s2, and then 3p5. Notice here, this is my valence shell because the principal quantum number is 3 for both. So these are my valence electrons. Right, and this has 7 valence electrons. What's the group number for chlorine? Where is it situated on the periodic table? We know it's a non-metal. We know it's on the right side of the periodic table, but what's the group number for it? The group number is always going to match the number of valence electrons. So that group number is telling you how many valence electrons are available for chlorine. So it's a group 7 element. So that means it has 7 valence electrons. So a lot of times when you see chlorine, it'll be written like this, where it has 3 lone pairs and then a single unpaired electron there. Right? And that's indicative of the fact that it has 7 valence electrons. All right, any questions so far? All right, let's do carbon and aluminum, and then we'll finish up there. And I want you to try these on your own: zinc, mercury, arsenic. And remember, when you get past 3p, the next available orbital is 4s before you go to 3d, right? So you're gonna fill 4s before you fill 3d. Right? Let's do carbon. Let me just do the same little trick I just did, since that's working. All right, where is carbon on the periodic table? What is, well, let me ask you this way. What's the atomic number?
6.
It's 6. So it's got 6 protons, 6 electrons. Right, so let's put that in. 2 here, 2 here, that's 4. Is that right? And then 2 here. Right, so it's 1s2, 2s2, 2p2. This is what makes carbon interesting. Because, and I'll share this about carbon since I teach organic as my main subject, right? These 4 valence electrons make carbon special. Because when you look at carbon, what it looks like is that it can only form 2 bonds, because when we look at this, you can see that you only got 2 unpaired electrons, so it looks like it can only form 2 covalent bonds. But in reality, carbon always makes 4 covalent bonds, unless it's some type of ion, whether it's an anion or a cation, which is possible for carbon. So let me just show you that. So we have a carbon, right? It's got 4 electrons around it. If it is neutral, it's going to make 4, just using the most basic substance, methane. It'll make 4 bonds like that. If it's positive, it'll have 3 bonds to it with a plus charge. If it's negative, it'll have 3 bonds to it with a pair of electrons. This is what we call a carbanion. Right, you remember this term, I'm sure, from the beginning when we talked about anions and cations, and this is what you call a carbo cation. Cation meaning positive, anion meaning negative. Right, so with carbon, it's a really interesting atom or element, because it can do a lot of different, it's very versatile. It can make double bonds, it can make triple bonds, it can make single bonds, it can form rings and cyclides and all of this stuff. So that's what makes carbon so special. And that's why organic is such a huge sub-discipline of chemistry, because carbon is just a phenomenal atom. It can do everything. If you think about your own body, most of our body is carbon based, right? All the proteins and all the different amino acids and peptides, and everything is carbon based, to the point where there's no such thing as any, how do I put this? Any human tissue, there's no human tissue that doesn't contain carbon, because all human tissue is made up of some type of protein or something like that. And so any tissue in the human body is going to be carbon based, because all your proteins are carbon based. So whether it's your skin, whether it's your liver, your organ, your eyes, your heart, whatever, the tissue that makes that up, the proteins that make that tissue, all carbon based. All right, so we're gonna let's do one more. Let's do aluminum, and then we're gonna stop. All right, so for aluminum, what's the atomic number? If you find it on the periodic table,
13.
13, good. So the atomic number is 13, which means what? How many protons, how many electrons?
Thirteen protons, 13 electrons.
Yes, so the atomic number is 13, so that's 13 electrons and 13 protons. It's not an ion, so the configuration is going to be based on those 13 electrons. So let's put those in. And if you notice, aluminum is group 3 on the periodic table. So what that means is that it's going to have 3 valence electrons. And any element in that column, in that group, is going to have 3. It might have more electrons, but at the end, the total number of valence electrons is always going to be 3. It won't change. All right, it won't change. So let's put that in. So 2, 4. Go ahead and fill this up. That's 10. That's 11, 12, 13. Is that right? So 1s, 2s, 2p, 3s, and 3p. So the valence, again, you're in the 3rd energy level. So that's a group 3 element. You got 3 valence electrons, and the electron configuration would look like this: 1s2, 2s2, 2p6, 3s2, 3p1. Right? Very important. I know it seems mundane, but it's very important because, again, your electron configuration is going to determine how you react. All of your atoms react differently. And the reason they do is because of how their electrons are organized around the nucleus. Right? So when you understand that part, then you understand why certain things do what they do. You can understand why transition metals are mainly able to accept electrons, because when you build the electron configuration for a transition metal, you see it has a lot of empty d orbitals. And so those d orbitals can accept electrons from other atoms. And what you can see why they behave certain ways. But everything is controlled by that valence shell. All right, so we're going to stop here, and I'm going to stop recording, and yeah, and I'll see y'all on